Good morning. We will continue our discussion of power amplifier output stage. So, in last two classes we have discussed about class A and class B, right. So, today we will discuss about the class AB. So, as we know that class A, it is operating for full 360-degree angle. The main transistor is on for full time period, right. But the drawback is that its power efficiency is poor. And class B, so if we think about the this full cycle, class A is on, right. And another thing is that it is having a AC superimposed with DC. So, it is on for full cycle. Now, in class B, it is on for only 180-degree phase, right, means half of the cycle. And another thing is that it is having only AC, only AC. This is having AC plus DC. So, this is class B. Now, in class B, what we found that its efficiency is improved, but it is having 0 crossover distortion. Why? Because at the 0 crossing it is not getting its VB on and it gets off for the certain dead band, right. So, how we can overcome that problem? So, what we will have to do? We will have to combine something, mixed both of them and make it a class AB. So, what we are doing? We are not adding a DC value of that large amplitude, we are only adding a smaller DC value. Okay. So, half of the DC value we are adding, so that Qn is getting its VB on during 0 crossing. Similarly, we are adding another DC voltage, so that we are getting VB on during other half cycle. So, in total we are providing a DC voltage of VBB, clear. So, what is the meaning? Meaning is that if your input is say above 0.5, you know that this transistor will be on. Main problem was when it was 0 to 0.5 or something like that. So, this extra voltage will take care of that problem. Okay. So, what is the difference? Difference is that we are not adding very big DC, we are adding a DC, but not adding a very big DC. Okay. So, what we are doing? We are just adding a small DC, right, and its conduction angle is greater than 180-degree, but much less than 360-degree. So, just little bit we are increasing, right. So, that is the now the transfer characteristics. Previously it was distorted, right, previously it was like this at the 0 crossing. Now, it is a linear. Okay. So, hope that we will not get that 0 crossover distortion. And what will be the output impedance? So, this is the NPN and this is the PNP. So, R out will be its emitter resistance parallel the emitter resistance of Qn. So, REN parallel REP, this will be the output resistance, right. And we all know that emitter node is having less resistance, right, and our target is to have less output impedance, high output input impedance or less output impedance. So, this configuration helps. Okay. So, this is one circuit. I am using a constant current and to generate these two diode drop. So, these two diode drop will create my VBB, right. So, this base voltage is above twice diode drop of Vi, right. So, even at 0 crossing this will be on, right, and this is this base emitter voltage you can think of another diode drop. So, 2 diode drop minus 1 diode drop. So, this is above diode drop of Vi. So, during 0 crossing this will be also on, right. So, the idea of having VBB by 2 above and VBB by 2 below of Vi is satisfied in the circuit. This emitter node is above 1 diode drop roughly, right. So, we can say that this will act as a class AB power amplifier. So, this is the biasing circuit to provide the small DC voltage apart from this AC signal, right. So, just like previous circuit, this is another circuit where we are having this base to emitter voltage and base to collector voltage and this collector to emitter voltage, which is providing this VBB. So, this VBB is provided by this potential divider as well as this emitter circuit. So, this is ensuring that this will be a fixed potential generated across this, okay. And this will ensure that this is on at 0 crossing and also this is on at 0 crossing, just like the previous circuit. All right. So, this is our equation for VBB from the potential divider circuit, right, total resistance multiplied by total current, okay. And from the base emitter voltage also we can calculate the VBB. Next is MOS based class AB power amplifier. So, we will be in previous case we have used both NPN and PNP. So, in this case we will be using NMOS and PMOS, just like the previous circuit, okay. So, output is taken from which terminal? Source terminal, right, output is taken from source terminal. So, this is a circuit of source follower, common drain or source follower, right. Previous one was, previous circuit was emitter follower, right. I am taking, so this is emitter follower, right. So, it is a circuit of source follower and we discussed that it is biased using a current mirror technique. So, what is a current mirror? Have we discussed before in previous class and before that? Okay. In previous class we discussed little bit. So, I will be just little bit repeat for the students who are new. See, I need to have a reference current, okay, and sometimes what we need to copy that current, right. For suppose multiple branch, I am having multiple branch, I need to copy that current. So, for this circuit we need current mirror. So, what is the concept? Concept is, suppose you will be use that current to generate a VGS, right. If I force this current to the drain terminal and I tie this drain terminal with the gate terminal. So, this current will generate a constant VGS, just like if we provide a constant VGS we will get a constant current. So, this bias will generate a fixed voltage, right. Why? Because ID is equal to half k n dash W by L VGS minus VTH whole square. So, if VGS is constant, ID is also constant, right. So, this will generate a constant voltage, so that IREF is satisfied. Okay. Now, if we, so this is my main circuit. If we add this node voltage to the gate of another MOS, So, what will happen, its VGS and its VGS they are same. So, ideally this should also carry same current, but due to channel length modulation this may little bit vary, because its drain voltage and its drain voltage are different, they are not tied. Gate voltage are tied. So, this gate voltage and this gate voltage they are same, but drain are not tied, right. So, drain voltage may be little bit different, and if you consider the channel length or lambda effect, then this ID and this ID may be little bit different. But if we neglect that, if we make it easy, and another condition is that its W by L and its W by L should be same, they should be identical. Okay, their threshold voltage, its threshold voltage, we are considering as if they are identical, same device. So, what will happen, in this branch also I will get ID is equal to roughly equal to IDEF. Suppose I take this gate voltage and connect it to another MOS having twice W by L. So, what do you expect, roughly how much current? Twice current. So, you expect a current of twice IDEF. So, this circuit is known as the current mirror circuit. Okay. So, you see this circuit is generating the fixed gate voltage for this. So, this is called current mirror biasing, this is for the NPN, this is for the PNP. Okay. Now, alternative circuit is that we can use some error amplifier or feedback, negative feedback to connect this circuit. Now, how to prove that this feedback is a negative feedback? So, you see this input Vi is given to the negative input and output is connected to the positive terminal, and this output is connected to the gate of the MOSFET. Now, let us assume that Vi increases. So, what will happen to the amplifier 1? This output will also increase. If this output is increased, this mod of VGS of QP, this will increase or decrease. This is Vs minus Vg, Vg is increasing. So, Vsg will decrease, right, because this is PMOS. So, if this node is increasing, this is fixed. So, this difference is getting decreased. So, if this difference is getting decreased, the current will decrease. If this current is decreased, this will balance the V0. So, this is acting like a negative feedback. Let us discuss about the lower half amplifier 2. Suppose V0 is increased, this output is also increased. If this output is increased, its VGS is also increasing. So, this pulling current is also increasing. So, it will pull more current from the output terminal. So, it will try to reduce the output voltage. So, we can understand that both of the cases V0, this feedback is acting as a negative feedback, right. Similarly, in case of V0 is decreasing, you can explain. Okay. So, if we assume that V0 is increasing, they will try to balance the V0. So, we can say that this is a case of negative feedback circuit, and which is helping to reduce the negative feedback, that output impedance will be reduced by 1 plus A beta. What is A beta? Suppose the gain of this is mu, do not get confused with this mu as the transconductance mu. So, this mu and it is GMRD, right. So, its gain is minus GMRD. What is RD? ROP parallel RL. So, ROP parallel RL. So, this is my feedback portion and this is my main gain portion, right. We know that it is A beta, right. So, here it is written as mu. Okay. So, we will be seeing that total output impedance will be reduced by, we know R out is reduced by 1 plus A beta. So, whatever was our previous R out, that was RL parallel ROP, and this is further divided. So, my output impedance is further reduced. So, it is helping to make a better output stage, this feedback. That was the discussion on class AB power amplifier. Okay. So, efficiency of the class AB amplifier will be also close to the class B, and maximum efficiency is roughly 78.5%. Okay. So, its efficiency is, you can repeat the class B efficiency, because you know that extra DC value is very small. Okay. So, you neglect, if you neglect that roughly, so you can consider same procedure, average power supplied up to 0 to pi only, and you can make the average current and average power dissipation and calculate the efficiency, which will be roughly 78.5%. So, if we discuss so far that A, B and C, if we discuss about efficiency, what is the maximum efficiency possible in class A? 25%, 78.5%, say it is, let us say this is also 78%, 78.5%, and this is class AB, right. And we have another, that is class C, that we have not discussed, but its efficiency is the highest and it is used in RF application mostly. So, we have not discussed that, but concept wise we discuss this. So, now let us discuss the transistor which is used for this specific applications to design the power amplifier. Okay. Now, you know that power amplifier, it is used at the output stage, and you know maximum power, and so the large current will flow, right. Output swing is maximum peak to peak and large current will flow. So, it should be robust, right. It should be, the transistor you are using to design a power amplifier should be able to handle more temperature, right. So, these are some important criteria, that its junction temperature should be able to handle high junction temperature, all right. Otherwise, what will happen? There will be damage to the structure. Okay. So, it should be able to withstand a temperature range of above 150 to 200 degree centigrade. Okay. And this is mainly this collector based junction should be able to withstand this heat. Okay. Otherwise, what will happen? That their silicon structure will be destroyed. Similarly, thermal resistance, that should be also able to withstand this temperature, otherwise what will happen? It will get destroyed. Okay. So, this thermal resistance, this is modeled like a so suppose this transistor is dissipating PD watts of power, okay, and temperature rise this temperature, we are modeling that this thermal resistance into the power is equal to temperature difference. So, it should be modeled like whatever the temperature range it can maximum it can go, and what is the maximum power dissipation, from this we model this thermal resistance. So, thermal resistance, if you calculate, this is del T by power. So, it is defined like this. So, depending on this maximum power dissipation and maximum temperature, we can calculate that what is its thermal resistance. Okay. So, this is a particularly for power applications, this slope is important, and they choose a device that is able to withstand that much of power as well as that much of temperature, that is it. Okay. Now, you know that there is a large heat will be dissipated. So, you need to dissipate it to the environment, so that you can cool it fast. Okay. the junction, the heat that dissipated heat should be, you should be cool it off quickly through the surrounding environment. Otherwise, if you hold it for long time, what will happen? There is a more chance that junction will be, silicon junction will be destroyed, damaged. So, we need some kind of cooler. Okay. So, if you see some power amplifier or power BJT or power MOSFET, you will be seeing that their casing is different. Normal package, plastic package, and this ICs, apart from the package, it is put in another case, and the collector junction and junctions are connected to this metal case. So, that the junction could be quickly cooled off. It could dissipate the heat through this metal case. So, this metal case is acting as a heat sink. There this picture is a popular TO3 package for power transistor. The case is a metal with a diameter about 2.2 centimeter. This outside dimension of the sitting plane is about 4 centimeter, and there are 2 holes for screws to bolt, and this acts as a heat sink. The collector is electrically connected to the case. Inside the case there will be the actual BJT, and the collector is connected to this metal case, so that this metal case can dissipate heat quickly. And there are some electrically insulating but thermally conducting spacer used between the transistor case and the heat sink, and in between some thermally conducting but electrically insulating. Otherwise, what will happen? They will short, right. This heat sink may be connected to the ground terminal. So, inside some material is there which conduct the heat only, okay, but not the current. And so, this case acts like a heat sink, and the objective is to dissipate the heat as fast as possible. Now, what is our safe operating area, right? So, we know that for power amplifier my current will be high, right. So, most of the power amplifier they operate at the output stage, and we have seen that it goes to full swing, right, VCC to minus V, right, twice V, its swing is twice V, right. Now, this transistor has some rating, right, particular rating, and we should choose the highest rating. So, the breakdown voltage is also specified. If you check the data sheet of any transistor in laboratory, whatever you are using, if you ask for the, or if you in Google, if you ask for the data sheet for that particular transistor BJT, you will be seeing that certain these all the specification will be mentioned. What is the maximum current IC, what is the breakdown voltage. Okay. So, this breakdown voltage you should choose as large as possible, so that your working region falls in safe region. So, what is the definition of this breakdown voltage? That if you should use below that voltage. So, this collected to emitter potential during open circuit, it should not go beyond this voltage. If you go beyond this voltage, what will happen? The transistor may be destroyed due to the avalanche breakdown, or the structure will get, because large current will flow, and due to large heat dissipations, all the internal structure they may melt, okay, and get destroyed, damaged. So, your thermal dissipation limit is around this is your safe point, and if you go beyond this limit, this is your secondary breakdown limit. So, this is your final breakdown. So, you should choose your BJT, so that its breakdown voltage BVCEO is much less than whatever range you are targeting. Your working voltage should be within that. So, what are the parameters for power transistor? So, what are power transistor? These are the rating is little bit higher than normal transistor. So, this power transistor means you know that you will be working on higher range, right, higher temperature, higher current, higher breakdown voltage. So, they are termed as power transistor. So, you expect high current, their beta is typically low. Okay. Normally, our normal transistor beta is around 100 or more than 100. So, this is typically low, around 30 to 80, few could be even much lower. At high currents, R pi becomes very small, Ft is low, your main target is large power, you are not going for high frequency. Okay. So, its unit cutoff frequency is much lower. Okay. So, as it is lower, its capacitance will be much higher, right, that you can guess that its size will be little bit bigger, so that it can dissipate heat. So, if bigger size, you can understand that parasitic capacitances will be also bigger. So, C pi and C mu that we discussed during the frequency unit frequency definition F t. So, they will be also larger. Okay. This collector ICBO is large, breakdown voltage BVCEO is large, typically around 50 to 100, and you say even some cases it can be as large as 500. So, these all are the requirements, these all are the parameters. IC max is also typically very large as and could be as high as 100 ampere. So, these are all specification of the power transistor or power BJT. Now, let us discuss a compound power amplifiers or compound composition. Okay. So, we can have certain variation in class AB configurations, and here some resistance R3 and R4 are included, and this is important, this is a Darlington pair. Have you heard this term, Darlington pair? So, what it is doing, you see that one transistor, its emitter is connected to the base of another transistor, their collector are shorted. So, what you can see, this collector current is say IC1. So, this emitter current is roughly IC1. So, you see now this I1 is equal to IB2, and you know its IC, it will be beta times IB. So, this is already beta times IB, this IC or IE. So, you are getting one beta multiplication here, you are getting another beta multiplication here. So, overall you can expect this device. So, if you model this device with a single device, how much is its beta? Is equal to beta 1 into beta 2. So, suppose these two transistor, this connection, this is not a real transistor, this is a model, that this transistor, suppose we are thinking that if we can replace these two transistor with a single transistor, then what should be its beta? Its beta should be multiplication of these two single transistors. So, this Darlington pair, you can understand, it is providing for large beta. Clear? What is the connections? Collector are shorted, the emitter of first one is connected to the base of second one, right. Okay. So, this is known as the Darlington configuration or Darlington pair, and this you can use, right. So, this circuit, suppose this circuit NPN and PNP, you can replace this NPN with a Darlington pair and this as a Darlington pair, and you will be having more beta, more gain. Okay. So, this is the application of compound, this structure is a compound structure, right. I have used 2 BJT to make this structure, and this compound structure is used in the power amplifier. So, what is the advantage of Darlington pair? It is providing larger beta. How? We can think that this is, if this is IB1, this is beta times IB1 and this is beta times IB2. So, this is actually this collector current IC 2 is equal to beta 1 beta 2 IB1. Now, we need certain protection. So, let us keep this protection circuit and let us come directly to power MOSFET. So, power MOSFET, in power amplifier design, the MOSFET structure is little bit different. Okay. Deliberately structure is make little bit different, so that it can withstand large current as well as heat dissipation, and it can withstand the power dissipation. So, what you can see that these upper two junctions, they are surrounded by a, this is a N plus doping and this is surrounded by a P region. Okay. And these two junctions are sorted and used as a source. Previously in normal structure what we had, this structure was source, this structure was drain, right, and this P region was continuous, right, P region was continuous, but in between this is a P plus region and substrate, and this lower region acting as my drain. So, the channel is in this way, the current flows vertically. In previous cases it was flowing horizontally, right. In this case the drain is below. So, the current this from this N junction, it goes and comes and collected to this terminal. So, this is the only difference. This MOSFET, this structure is known as the double diffused or DMOS transistor. This structure is, you see there is a one diffusion and there is another diffusion, double diffused. Okay. Previous normal MOSFET, it was like this junction, right. But here as if this is a separate, these junctions are separate, no continuation. This device is fabricated on lightly doped N type substrate. So, this substrate is N type and this is P type. Okay. So, structure is, you just understand this, that the structure is different. So, what happens that the current flows vertically, okay, and it has a high current capability. Its breakdown voltage also very large and it could go up to 600 volt. So, the current, it flows vertically down. In normal MOSFET we have horizontal current flowing and this is flows vertically down to the drain. So, this is a different structure for power MOSFET. Its current, you can see the plot, it is quite similar like the normal power MOSFET. Normal MOSFET ID versus VG, it looks like the same, but it suffers from a phenomenon that is known as the velocity saturations, and due to that it has its maximum current that get reduced due to this velocity saturations. Okay. And this application is this D MOSFET or double diffused MOSFET, its application is in the power applications. Okay. It can withstand more current and more breakdown voltage. The normal equation, current equation satisfied are same. So, we have covered the power amplifier, both class A, class B and class AB. Class C we just defined what is the class C, but we have not gone it in details.